Hi, we're going to be taking a look at section 3.4, number 18. That's on page 137. And in this problem, we're given a graph that shows the velocity of a model rocket. And we want to be careful to notice that the axes tell us that we're looking at a graph of velocity. And then, based on this graph, we're supposed to answer a large number of questions. Now, as always, when we're given a graph of velocity, the first thing that we're going to want to do is to make for ourselves a number line showing where the velocity is positive and where it is negative. And I got to fix my graph just a little bit. There we go. And so the first thing that we're going to do then is to observe the places where the velocity is 0. Now, because we're looking at a velocity graph, then the places where the velocity is literally 0, where it crosses the axis, are those places. And the velocity is positive in this region and negative down here. Notice that I did not consider the slope of the velocity, but the values of the velocity themselves. Okay, now armed with this, I'm ready to start answering questions. First question, A. How fast was the rocket climbing when the engine stopped? I've got to look at this graph and figure out when the engine stopped based on this. And here's what I observed. I observed that between 0 and 2, the speed of the rocket keeps on going up. And then right here at t equals 2 seconds, the speed of the rocket begins to decrease. So I conclude that the engine stops here, because that's when the speed stops going up. And we've got to spell stops correctly. Now, after the engine stops, then we see that the object begins to, experience what we call free fall. That is, only gravity is pulling on it. But please notice that the velocity is still positive for this entire portion right here. And then it goes negative. So this time, which is t equals 8, is the time when the rocket reaches its maximum height. That's our slogan, right? Our slogan is that we stop at the top. And sure enough, the velocity is 0 right when we reach our max height. So, how fast was the rocket climbing when the engine stopped? When the engine stopped is t equals 2, and I go up and I see that my speed was just under 200. Looks like it's going to be 190 from the graph. So 190 feet per second, and there I'm pulling the units straight off the axes. Part B, for how many seconds did the engine burn? Well, that's during this time period, so that would be 2 seconds. Part C, when did the rocket reach its highest point? Again, with stopping at the top, rocket reaches its max point at t equals 8 seconds. When did the parachute pop out? Now, that's an interesting question. Let's see what we have here. Again, for all of this time, the rocket is experiencing what we call free fall. It's coasting upwards under the influence of gravity, and then from t equals 8 onwards, it's coasting downwards under the influence of gravity. And right here, right at t equals 11, looks like from the graph, the rocket experiences a sudden change in its velocity, and that sudden change is caused by the parachute popping out right here at t equals 11. So when did the parachute pop out? At t equals 11. How fast was the rocket falling then? From the graph, it looks like this velocity here, v of 11, is negative 90 feet per second. How fast is a question about speed, and so therefore we're going to say that the speed, the absolute value of velocity, is 90 feet per second. That's how fast it's falling. E. I'll do this in green. How long did the rocket fall before the parachute opened? Well, that's just a matter of subtraction. It was falling from 8 seconds until 11 seconds. So 11 minus 8 is equal to 3 seconds. And then finally, when was the rocket's acceleration the greatest? When was the acceleration constant? So our reasoning is that acceleration is the derivative of the velocity. I'm going to be looking for when the derivative or the slope is the greatest. And I notice that the curve appears to be the steepest, the slopiest, right up here near t equals 2. And so we're going to say that the greatest acceleration is going to be at t equals 2. And when is the acceleration constant? Now I'm looking for constant slope. You can see that that occurs all throughout here, from t equals 2 all the way to t equals 11. And just as a bonus question, we wonder what that constant acceleration is. And so we go back to the graph and try to read off the slope from the graph. At t equals 2, we have a velocity of 190 feet per second. And down here at t equals 11, we have a velocity of negative 90 feet per second. And so our change in velocity over change in time, the acceleration, is going to be final minus initial, all over final minus initial, 11 minus 2. And that gives us negative 90 minus 190 is negative 280 feet per second divided by 9 seconds. And when you actually do the math, this comes out to negative 31 feet per second. And that compares very favorably to the official value of the acceleration of gravity, which would be negative 32 feet per second squared. None of this computation was required by the problem. We just did it because